I will talk about the stellar kinematics around galactic center, and this work is performed by Gravina, Salvatore Capozziello, me, and Borka Jovanovic. And Gravina is one of the students that use Erasmus mobility program. Our project, it is a project between Vinča Institute, because Vinča is part of the Galactic University, and University in Naples, Federico II. And she spent 3 months in Vinča Institute and worked with Vesna and me on some part of her research. Supervisor for this work is Professor Salvatore Capozziello and Vesna Borka Jovanovic. I helped in some part of this investigation, and I will present her work. Also, second student, Anna, was doing connected thing, and after me, Vesna will present work of second student. First, I will say something about motivation for this work, a few basic things about extended theories of gravity, then I will mention S2 orbit and how we simulate, then I will present results, and at the end I will give conclusion. In this picture, we can conclude that in the beginning, velocity grows linearly with radius, but after some distance, it is roughly constant. This is observation. If we take only Newtonian theory, we will get a curve designated by this dashed blue line, and we see big scatters. We can solve it in 2 ways. One way is to introduce new substance, dark matter. Other way is to change the fundamental gravity law, or modified gravity. And in the right panel, we can see that using a relatively similar extension of general relativity, R on N gravity, we can explain very well this observation. Extended theories of gravity is in some way modified gravity, but it is extension of general relativity. Extended theories of gravity wants to save general relativity in that way that they want to cure its shortcomings. In the most simplified case, in the f of r gravity, we assume a generic function f of Ricci scalar r. We suppose that it is an analytic function, and then we have to search for theory that is have a suitable behavior at different scales: solar system scale, subgalactic scale, galactic scale, cosmologic scales, and for now we have lucky that we have astronomical data for 3 scales: for S2 star scale, for galaxy scale, for fundamental Fisher relation, and for larger extragalactic scale for fundamental plane of galaxy. And we can then test these different gravity models and find find parameters of these different extended gravity models that is in good agreement with astronomical observations. And Stefania's task was to first make derivation for scalar tensor theories of gravity. Effective action is more complicated than in the case of F of dark gravity. This is effective action. F is an unspecified function of curvature invariance, and scalar field is designated by phi. And if we want to know dynamics of this gravity, we derive the field equation. In general case, we varying the effective action first in respect to metric, and also we varying the action with respect to scalar field and get field equations. And what we in this Stefania take a specific case for a function f of phi r. She takes this equation, and we take also specific arbitrary functions phi of phi and v of phi in this form when psi is completely constant, and lambda gives the self-interaction potential strength. We take this form because this form was relatively successful to some cosmological investigation. And after some mathematical calculation, we get this for scalar tensor potential in a weak field limit, this expression, and we also calculate perturbing potential in case of scalar tensor theories, and we get this expression. And now we want to determine parameters of this potential in a way that we want to see what is agreement with observation. Using astronomical observation, we will fit these parameters, and we will extract the best values for parameters. Parameters will be lambda, psi, n, and n. And we also showed that phi 0 is very close to 1. It is not, if we take, for example, 0.5 or 1.5 for phi 0, it is very weakly influenced on the result, and we take values close to 1. And we take one set of astronomical observations that we have S2 star orbit. This is a structure of the Milky Way, and this compact radio source, Sagittarius A, has its position is there, and it contains over 3 components: Sagittarius A East, Sagittarius A West, and Sagittarius A asterisk, which is a very bright radio source. And probably it is, in fact, a supermassive black hole. And S stars orbiting close to this supermassive black hole, and we one very young, bright, the brightest member of this S star cluster is S2 star, and we take data for S2 star from observation, which are publicly available on online version of the paper from Astrophysical Journal from 2009. It is now there are some new results, but we take this old one. It is observations are performed using new technology telescope in Chile and very large telescope in Chile, and this is astrometric data, and we can see that orbit is not closing. And also in the paper from 2012 in Science, they also measured that orbit is not closing. Why it is important? Because if you take only general relativity, precession will be very small, 0.18 degree, and here it seems it is bigger. And this is, for example, data from last year in Astrophysical Journal. We also can see that they also measured that the orbit is not closing. And we performed simulation, take this scalar tensor gravity potential and try to obtain a precession angle. For this simulation, we take that distance from S2 star to the central black hole is 8.3 kiloparsec, and we take that the mass of supermassive black hole is 4.3 million of sun mass. And we make a simulation in a scalar tensor gravity potential, and we first calculate true orbits, but in order to compare it with observations, we have to project them on the observed sky plane, and to calculate apparent orbits, we use these expressions to do it, and then for potential, scalar tensor potential, we take parameters of this potential, phi 0 mn and c and lambda, and take for phi 0 positive real number close to 1, perform fitting procedure. We take initial values of true position and orbital velocities from astronomical observation, then using this procedure, and we calculate reduce chi square, and we find the values where it is better agreement with calculation if we use scalar tensor gravity than if we use Keplerian orbits. And we also find the expression for potential in scalar tensor gravity model, and we calculate precession angle according this relation. We do it numerically because it is very complicated to do analytically. For f of r gravity, it can be done. We get some hypergeometric function, but in this case is even more complicated, and we do it numerically. And for example, there are some orbits of calculated orbits of S2 stars. This is 45, for example, orbits. This is upper panel right 90 periods, lower panel left 120 periods, and so on. And we take these parameters that we get from from fitting procedure, and also we make a comparison between data by blue dots between fitting orbit in scalar tensor gravity and between Newtonian orbits. And we take these parameters by fitting procedure, and we get a better agreement for fitting orbits than in the Newtonian case. And we calculate using this expression precession per one period, and we get some values between 2.2 and 2.8 degree, which is much bigger than in case of general relativity. This figure shows us that the precession has the same direction like in general relativity. That's why we make a lot of calculation for a lot of periods, and also this will be second way to calculate precession angle if it is 45 orbits and this is around 90, something more than 90 degree. We can see that it is bigger than 2. What we can conclude? We can conclude that using that investigated S2 star orbit in scalar tensor gravity potential, we obtain the most possible value for parameters lambda and c, and we take parameters m and then in advance. And for different combination of n and m, we calculate parameters lambda and psi, and we get precession. It is in the same direction like in general relativity, but the precession has a bigger value, we think, which is in accordance with these observations by VLT telescope. And we believe that our approach can be used to constrain not only different extended gravity models, but also different modified gravity models. This approach for S2 star, and then we have also for fundamental plane and for baryonic Tully-Fisher relation. But if it is a larger scale, then difference between general relativity is bigger and bigger, and maybe it is easier to make some constraints. But in all scale, we have to test it some gravity model. And this is, in fact, a master thesis of Stefania Gravina. I presented it.
Any questions? About the fitting that you mentioned, the chi-square fitting.
Yes.
So you were just fitting the orbit on the data.
Well, fitting procedure. Okay. First, we take initial value of true positions of orbit of astrometric data and orbital velocity. We have from internet. We find this value, and then we calculate positions x, y, and y, xi and yi, and the velocities of S2 star along this true orbit, using numerical integration of equation of motion, of but in scalar tensor gravity model. Then we obtain corresponding position in apparent orbit, and then we compared it position and also for radial velocity, and we use this expression for reduced heat square. And we find positions when he square is minimum. In fact, for Keplerian orbit, we get if we take for Keplerian orbit, we, for example, get he square 1.89 for this data. If we take Keplerian orbit, but we try to, but if we take modified gravity, we then get in parameter space some areas when he square is less than 1.89. It seems that it is a better agreement with data than in the case of Keplerian orbit. And then we calculate, then we take these parameters in this area, which has a better agreement with calculation, with astronomical observation and plot orbits. In fact, second master thesis are more connected to this. Vesna will present master thesis of Anna, and you will see the areas which is better agreement than in Keplerian case using this fitting procedure.
Yes, but my specific question was, I mean, as I can see from this equation, you just separated the fitting procedure for x and y axis, but if you're having orbit, could you do it? I mean, because it's not a regular function. That was my question.
Yes, but all of them are measured at same epoch. So
yes.
At one epoch we have measured x and y coordinates. So this is the standard, I think, procedure for fitting binary stars or something like that. You always have two coordinates, x and y, measured at same epoch, observational epoch. So these are the fittings as I understood at the observational epoch.
Yes.
You integrate
yes.
all orbits and then
Yes.
take them at observational epoch.
This is a standard procedure. This is nothing that for fitting procedure we take a standard procedure for fitting.
Well, if I understood correctly, you have used the two-body approximation.
Yes, we believe that, for example, like in a solar system case, we can, if we calculate something between Earth and Sun, we can omit other planets in a very.
In the solar system, you cannot omit them.
Okay, for some
mistake. That was my question. Whether your fit would improve if you would take into account
yes.
also maybe other
yes,
stars.
if we
because
take n-body
stars,
simulation with other stars, for sure it will affect, but I think very little.
Well, at least in the projection, which
yes.
you showed in the plot,
yes.
the motions of the stars in the vicinity of the galactic center, what I've noticed is that you had some very close approaches of the stars. Even the symbols were joined and so on. So I'm wondering whether it would be.
We also in the future we will do n-body simulation, but
yeah,
we also try now some extended mass distribution and try to calculate in this case what we get for parameters. And maybe it is the best if we said that this orbital precession and is in fact that we obtain is in fact the biggest value. In reality, it will be something between general relativity and this, because of these different effects.
Because if I understand well, your extension of the let's say Newtonian potential or whatever is actually acts as a perturbation in the
yes.
standard Newtonian
yes.
gravitation field. And it is bigger than the usual, than the perturbation or perturbative effects of the other bodies in the dynamical system.
Yes.
Isn't it?
Yes.
Okay.
So I just want to add, you have, I think, at this level of precision, what is the dominant is in fact black hole.
Yes.
And smaller black holes, if they are or neutron stars, they cannot be maybe these points that are not good fitted, but it is not dominant, and at this level of precision, it cannot be studied well. So, for example, gravity instrument which is made for this purpose, and which will have 10 micro arc seconds for 15 minutes star. In fact, S2 is in gravity. It is made for this purpose, and probably it will give an answer for. It is intended to detect the smaller black holes of the stellar origin or neutron stars. Since Stefania is just starting her career, she will probably work on this data. The data, in fact, it started. First observation of gravity was last year, so it is quite new. It will be available next year, and next year is very interesting because S2 star is going through
Galactic center.
Yeah. Okay. So it is, in my opinion, the gravity. It has a name, gravity, and it is intended for study of gravity potential. More questions? Thank you very much. So.